Okay, thank you. Yeah, so my name is Mike Perucca, and I am from Lucid Software, and I'm going to talk about constraint typing with predicates. And it is something that I have been focusing on a long time, and recently with the release of Scala 3, I found some satisfying ways to design APIs that are safer through constraints. So as an example problem, oh, just a second. So as an example problem, here we have an absolute value function. This is built into Scala. And if we call it on some numbers, usually it works. So for example, absolute value of 42 is 42. Absolute value is -7 is 7. But if we try to call absolute value on the minimum integer, it will overflow and we will get the minimum int back. And so we will have a bug in our program. Also, if we try to call absolute value on a random integer, it might fail because we might have the negative minimum integer. So we would like to find a safer way to have an absolute value function. And one way we can start is by designing a constraint that represents the not being the minimum integer. And we just design it with a trait, and we pass in the value as a type that we don't want being the minimum int. And so we can kind of attach that constraint to a function. So if we design a safe absolute value function that is given an int, we also want to pass in a guarantee, and guarantee as part of this library that I've been working on, that it is not the minimum int. So that I.type, the singleton type, is not minimum int. And if we have this guarantee, we will go ahead and call the built-in absolute value function. And we know it's safe because they've given us a guarantee. But how do we pass in a guarantee? If someone wants to call our safe absolute value function, what are they going to put in for these spots? And so one way is to just trust the constraints. So there's this guarantee.trust that will just believe whatever we want it to believe. And so if we call in 42 and we pass in a trust, we will get back 42. If we call our safe absolute value function on -7, we will get back a 7 with this trust. But we can also trust things that we should not trust. So if we call safe absolute value on a minimum int and we pass in trust, we will still get the same runtime bug of overflow. And if also we call trust on a random integer, chances are it won't have a bug, but sometimes it might, just if we get this int min value. So we don't always want to trust. So another way we can do it is through runtime checks. And we can do this through type classes. So if we have some type that's an int, as long as we can get the value of that type, that int type, we can have a runtime check for it. And the runtime check is for a not min int. And all it does is gets the value of this int out. And if it's not equal to an int min value, that means the runtime check has passed. And so with that in place, we can now, for example, get a random int. And we can call guarantee.runtime check and pass in the guarantee we are looking for. And if we get a left out of this, this returns an either. So if we get a left out, we have actually a guarantee of the opposite thing of what we need. And so in this case, we don't have the right guarantee to call our safe absolute function. So we have to do something else, maybe print line, hey, we can't call safe abs. But if we get a write out, that means we did get the guarantee out that we need, and we can pass along this guarantee to our safe abs function. And we don't know which one's going to happen because this is a random int. But that's not always what we want to do, because sometimes we have a static value. So this is like the minimum int that we've assigned. And because this requires a guarantee, we need to pass in a guarantee. And the only way we can get it right now is through a runtime check. So even though we know that this is what is going to happen, our runtime check doesn't know that until runtime. And it's the same problem with succeeds. If we know it's going to succeed because we have a 42, we know that it's going to enter here when we look at the code, but we're still doing a runtime check. So the runtime, the type checker cannot help us. And so we would like to have constraint checking at compile time. And we can also do that through a type class, but we do it through inline. So inline will run the code that we give it at compile time. And so if we have a compile time check on an int, some type int, we can create a compile time check for the not min of that value. And the way we do that is with this helper, a compile time check not min, given that int. And the way we implement it is we have to create an inline function that returns either true, false, or null. So it might be null. We might not be able to know because it might be an expression. And if it's an expression that we can't evaluate at compile time, we'll have to return null, saying we don't know. And the way we've implemented it here is through a macro. And all our macro does is it just calls into our runtime check. So it tries to extract a constant out of the A that we've been given. And if it can, then we're going to go ahead and call our runtime check, but we're calling this runtime check at compile time. So we're just running the check before the code runs. And so if we have that in place, we can go ahead and call safe abs on 42, and we can do guarantee.compile time check now. And this will work. It'll give us a 42. It'll compile. It'll work with the -7. If we try to call it with the minimum integer, we will get a compile time error because our check will fail, because it will see that this is the minimum int. And interestingly, if we try to give it the random int, this might fail. And so we get a compile time error because we want to make sure that we're being extra safe. And so we won't let the program compile if it can't tell if it's going to work or not. Now we can make if we want to take this farther, we can make the compile time, we can make this compile time check generic. So we can create just a trait that takes two values and checks if they're not equal to each other. And so with that, we can now use this in a more generic way. So how this could work is if we have, for example, a fraction type. And a fraction has a numerator and a denominator. And if we want to make a fraction, we need a guarantee that the denominator is not equal to 0. And if we can provide that, then we can create a function or a fraction. And we might want to have a method on our fraction that gets the whole number part out of our fraction. And the way that works is dividing the numerator and the denominator. But if they try to call this function, we want them to also guarantee that the numerator is not the negative min integer and that the denominator is not equal to -1. Because if that were to happen, we would get an overflow and we would have a bug. And we don't need to check that the denominator is not going to be equal to 0 because we've already done that in the constructor. So we have all the guarantees we need now to do that. But it doesn't work as nicely as we would like. For example, if we create a fraction of 1 and 2, we can go ahead and create that because this guarantee.compile time check will see that denominator is 2 and it will see that it is not 0. And so that will work. But then if we try to get the whole number part out of this fraction, it's going to be 0 because 1/2 is less than 1. But if we try to call it, our guaranteed.compile time check won't work because the fraction has kind of forgotten that it was constructed with a 1 and a 2 up here. And so we want some way to remember that we have created this fraction with a 1 and a 2. And so there's a different way that we can construct our data types. And here is one way. We can put the types, like the values, into types. So if we have a fraction, let's go ahead and expose the numerator type and the denominator type as ints in the type of fraction. We still have the guarantee that the denominator is not equal to 0. And now the whole number part still has the guarantees that the numerator is not equal to the minimum integer, or the denominator is not equal to a -1. And we can still do the division because we can get the value out of the numerator type because we've specified that we need to be able to call the value of, and we can get the value of the denominator type because we've also said that we need the value of. And now if we try calling it, we construct our fraction a little bit differently by passing in the types. And because it can get the values out of this, we can now store the fraction as a value, and the guaranteed compile time check works because it sees that 2 is not equal to 0. And then later on, when we call fraction.whole number part, it remembers that the numerator is 1 and the denominator is 2, and this will work with a compile time check because it has all the info it needs. Even more interestingly, it can also handle unknowns. So let's say the numerator is some random integer and the denominator is still 2. Well, we can create a fraction, even though it doesn't know the denominator, we know that even though it doesn't know the numerator, we know that the denominator is not 0. We know that it's 2. And because we know that, we can create the fraction, and we can call whole number part even though we don't know the numerator, because the guarantee that it requires is that the numerator is not equal to a negative min int. We don't know this part. So this might actually be true, but we don't know. Might be false. But we do know the denominator is not equal to -1 because we remember that it's 2. And since this part, just knowing this part satisfies the OR, we are actually able to call guarantee compile time check, and we can do the compile time check that it's safe, and it will let us call this. So other things that we can do with this library is we can have some constraint combinators. So we can do like nots, XORs, implies, exists. We can do ands and for alls. And all of these things compose and work nicely, just like a regular Boolean equation that we could write. And constraint normalization also works. So if we need a guarantee of not some constraint A, that is seen as the same thing by the type system as a guarantee of A. And this works because it knows De Morgan's laws. And so we can have really long and nested Boolean equations that all flatten out to a long list of Boolean terms that get grouped together, and subtyping rules are remembered, and it works out nicely. We can also do unbounded collections. So maybe we want to have a constraint of numbers being increasing, and this works, and it goes past the limit of 22 that tuples used to have, like in Scala 2, because Scala 3 now has an unbounded tuples, and we can still get the values out of those tuples at each position. And so if you're interested in these things, I have a GitHub with, it doesn't have any documentation at the moment. This is still in early stages, but I found that the constraints work a lot nicer than I've experienced in the past with other libraries that do refinement types. I like having the constraints as a separate value. I feel like that helps us compose our constraints better, and it makes it so that we don't need to change the actual underlying data types through maybe opaque types or through tagging. We don't need to do that with this library. So thank you, and that's all I got for my talk. If anyone has questions, you can go ahead.